Hi everyone. Hopefully you have a good weekend. Welcome back. And this is we are very, very happy to have Sean to be back to teach us more about the geometry interpretation for the delta theorem. And this is a part two of the series. And just to remind you guys, this is the only lecture this week. Because like Thursday, that will be the Juneteenth. And then we will resume next week as well, next Tuesday. All right. So I'm not going to take too much of your time, Sean. You can take over.
Okay, thank you so much again. So yes, so last time, uh, or first, just to remind you, the overall goal is to explain this identity of symmetric functions using the geometry of affine Springer fibers, and and just kind of slowly building up the pieces of this. So today still talking about t equals 0 specialization. Is the background noise too? Can you hear the ambulance?
No, everything is really good.
Good, okay. So still working with t equals 0 specialization of this identity. And really just like trying to understand both sides as polynomials, or really just the right-hand side as a polynomial. Um, so last time I defined these two varieties. First is the spanning line configuration space of Pawlowski and Rhodes. So I labeled them with their last names. So just n tuples of lines in CK whose span is CK. And we talked about how this is an open subvariety of a product of projective spaces. So it's smooth, but non-compact. And then this other variety that I like to call the delta Springer fiber. Um, so it's the space of partial flags, initially complete. So adding up one dimension at a time, a line contained in a plane, contained in a three-dimensional subspace. But you only take up to dimension n, and then all sitting inside of this large dimensional vector space. And then we have an operator, a nilpotent operator. So n is a nilpotent matrix with Jordan type equal to a rectangular partition. And I kind of explained how to construct that. You start with a rectangle and label the cells with vectors, and then define the nilpotent to just move the vectors over to the right, and then when you get out of the rectangle, it goes to 0, so that's why it's a nilpotent operator. I might sometimes denote this partition in this notation, so all of the parts are size n minus k plus 1, and the exponent just means like repeat that k times. And then we have these extra conditions where the nilpotent operator sends the ith subspace into the ith subspace, and that the kernel, which I visually explained as like the span of the vectors on the right-hand side, is contained in the nth subspace. And so this is a closed subvariety of the partial flag variety. Yeah, where you're building up the flag one dimension at a time, but then there's a big jump of n dimension of that size. And then I stated these two theorems, one of Pawlowski and Rhodes, that the Poincare polynomial of the first is equal to the so what you get by setting, so this is first you set first you set t equals 0 in this delta theorem symmetric function, but then you also take the m1 to the n coefficient, and you get that polynomial. If you reverse it, you get these two Poincare series. And I just wanted to,
Ask you a question about that I meant
yeah,
this last time. Um, so in this special case, your like area is 0 and then you take a special coefficient. Is there some variation, like a similar trick you can do with div? Like I say like div is some specified thing. And does that encode any geometric information?
I don't know.
Okay.
For me, dinv is like computing cell dimensions, and then area is something completely different geometrically for me.
Okay.
So yeah, I don't know what div equals 0 could mean in terms of like cell dimensions.
So that's like you think of it as cell dimensions in your maybe like delta Springer fiber, and that's why it is natural for that to be the variable, is what you're trying to tell me.
Yeah, I guess in the affine Springer fiber model that I'll show later,
Mhm.
div 0 would be like you're taking, okay, codimension 0 cells, um, and then uh, in these different connected components of the affine Springer fiber. Maybe I'll try to answer it later
Okay, thank
when I
you.
define
Thank
the
you.
affine Springer fiber. Um, um, okay, so I'd like to like briefly explain why, like, how do you prove such a formula, and just thinking about the right-hand side. So in order to compute these Poincare polynomials, usually you would try to find what's called an affine paving. So an affine paving of a variety is a filtration of X by closed subvarieties. So X is, say, some top dimensional piece, or top, like Xn is the full thing, and then sitting inside of it is some closed subvariety, and then another closed subvariety inside of that, and so on, until you get down to the first piece, and then sitting inside of that is maybe the 0th piece, which is empty. Um, so that each difference um, is um, is isomorphic to affine space. So just C, some power of C, some affine space, um, for some mi. So the dimensions could vary as you go along the filtration. Um, and these differences are what are called cells of the affine paving. So it's kind of it's sort of a weakening of CW decomposition, but keeping within like so that the cells are algebraic subspaces. Um, and so why do we care about affine pavings? So if your variety is compact and has some affine paving, then you can use it to compute the Poincare polynomial. It's just the generating function over the cell dimensions. Um, and so the assumption compact here is because first, so for experts, first you would really, this is the affine paving is really computing the Borel-Moore homology, but then if X is compact, Borel-Moore is the same as homology, and then you can use the universal coefficient theorem to say that homology and cohomology have the same rank in each graded piece. If X is smooth, then you can use Poincare duality to get the ranks of the cohomology groups. And so what does that have to do with the combinatorics of involved in the delta theorem? So we proved that this space, the delta Springer fiber, has an affine paving. So in which each cell contains exactly one torus fixed point. And the torus fixed point corresponds to some leaning stack word labeled deep path. With area 0. And so that like there should be some translation between these cell dimensions, the MIs, and the combinatorics. And it turns out that the codimension inside of the variety of the cell is equal to the div. And if I call this identity star, then star follows immediately from this fact. And so the fact that we're computing codimensions lines up with the fact that we had to reverse as a Q series. And these cells are given by, so the cells are given by intersecting this variety with Schubert cells. And I won't define Schubert cells yet, but I'll give an example of how that kind of computation works.
Sean, can I
Yeah.
ask you a quick question?
Maria?
Yeah. So the when you're talking about area and div here in WLD stack, so there's some kind of bijection that turns this into like OSPs and cocharge, right?
OSPs, like
Or sorry,
in
whatever the statistic is on the OSP.
inversions
thing.
on OSPs.
Okay.
But then like it's the kind of bijection that you just have to do a few examples to realize that it's the same statistic as
Okay.
in on these like on the word labeled guys.
Cool. Thanks.
And the same statistic on the Fubini words. And yeah, I wanted to kind of point out like why should one care about finding some geometric interpretation like this? Like why realize some combinatorial polynomial as a Poincare polynomial? And the reason why I cared initially was because this theorem and the fact above tells you that different geometric decompositions of the variety can give you genuinely different combinatorial formulas for the polynomial. And I have used this fact a couple of times. So for example, like expanding these symmetric functions in terms of Hall-Littlewood polynomials, you can do that. In fact, my only proof of that kind of identity is using geometry, or not for this case, but there are some other varieties, some slightly more general varieties, where my only proof is geometric. Jim and Brendan and Mark have combinatorial proofs in this case. But you can alternatively see it geometrically. Okay, so how do these cells work? Let's specialize to n equals 3, k equals 2. Then I'll just give you that the dimension of this variety is 2. There's a formula for it, and it happens to be 2 in this case. And say you could start with one of these leaning stack pictures. And area 0 means the stack matches up with the path. And under the bijection that I drew last lecture, this corresponds to a row strict filling where you put the first column in the first row and the second column in the second row. So this is an element of the row strict labeled rectangles. And then we had a bijection to torus fixed points. And I'll remind you, how did we do that? Well, we thought of the nilpotent operator as you take this same rectangle, but then fill it in with basis vectors. And the nilpotent sends vectors over to the right. And the one here means I put the first column is in E2. The 2 means I jump to E4. And then the 3 means I go to E1. And then to get the cell, we take the corresponding Schubert cell for that matrix. So I'll put the ones in the same positions. And then the way that the corresponding Schubert cell works is you put zeros to the right and below each one. So below and to the right of each one. And then in the remaining spaces, I have some free parameters. So I can put ABC for some arbitrary parameters. And then to get the cell of the variety, I then intersect it with the variety. And remember, part of being in this variety is that n acting on the span of all 3 columns, n acting on the span of the first I columns is in the span of the first I columns. And maybe I'll leave this as an exercise. that these conditions imply that A has to equal C. So it might cut down, it might give you some extra equations that cuts down the dimension of the cell. So what the cell actually looks like is we have A, B, 1, 1, 0, 0, 0, and then A, 0, 0, 1, 0 for arbitrary A and B. And so this cell is isomorphic to C2. And then, so it's telling me the theorem above is telling me that the codimension should equal the dinv. And indeed, so the dinv here is 2. Wait, sorry, the dinv is 0. And on this side, the codimension of the cell is the dimension of the total space minus the dimension of the cell, which is also 0. So these two things match. Okay. Yeah.
Just a quick question. I think above you said that the cells are the Schubert cells intersected with the delta Springer, but you just wrote Springer 3-2 over on the right. I don't know if it was
Oh,
missing
sorry.
something or if it's the same thing in this case.
Yes, I kind of changed the notation in my notes several times, and
yeah.
sorry, thank you.
But I mean, delta Springer basically just means like it's this specific n, and also you have this kernel is contained in Vn condition. And does that like affect how the exercise works out? That extra condition?
Yeah, so I mean, the particular Schubert cells are chosen so that the particular Schubert cells are chosen so that that other condition, the kernel being in Vn, is always true. So you can see that like no matter what A, B, and C are, the span of these two vectors is the kernel. So when you do the equations, it's like you don't even have to worry about that.
I see.
Condition.
It's like in this construction of how you go from the stack to the cell, like you actually end up not having to worry about that last condition.
Right. It's really just it's like the right Schubert cells or like the right ordering on the vectors so that it's just, you know, some cells will just, you won't even see them at all because the torus fixed point doesn't even correspond to one of these combinatorial objects.
Right. Okay. Thanks.
Yeah, right. Like I can't see all of what Jake wrote, but yeah, all of the
I can say it, but it was similar to what I think I wrote it at the same time you did, that the point is like the Schubert decomposition is chosen so that the flag is very compatible with the operator n and the Jordan basis for it. And it seems like how it plays out in this language, though I haven't heard, like this isn't how we thought about it at the time. So the stuff about torus fixed points is new to me, but it seems like the point is that the other Schubert cells would just be disjoint from the delta Springer variety.
Right. Yeah, exactly. Yes. Okay. So the next goal is to basically upgrade this from polynomials, from Poincare polynomials to SN actions and Frobenius series. So how do we see, basically, how do we see you know, this symmetric function as a symmetric function, not just like taking a particular coefficient, but all of the coefficients simultaneously. So in order to do this, I'll define Frobenius character next time, but so I wanted to build up, kind of give a crash course on Springer theory to lead us to connecting these delta Springer fibers to classic Springer theory and how you can use that classic Springer theory and apply it to this combinatorial situation. Okay, so the basic setup of Springer theory is you have the nilpotent cone, which is the space of nilpotent n by n matrices. I will try to use a curly n for the space and a straight n to denote a particular matrix. FL1 to the n will be the complete flag variety. So we saw partial flags before, and this is just where Vn matches up with the whole space. And I might sometimes denote this as 1 to the n to save some space. It turns out that this is a variety because nilpotent is an algebraic condition on the entries of the matrix. One way to say it is like when you raise the matrix to the nth power, you get the zero matrix. But really you have to take the radical of those generators. And it turns out to be singular, and it has a direct connection to the flag variety. So we will also need what's called the Springer resolution of the nilpotent cone, so one way you can define it is as the cotangent bundle of the complete flag variety, but I like to think about it more concretely in terms of flags and nilpotents. So it turns out to be isomorphic to the following space of pairs. So you take complete flags together with nilpotents. Together with that condition that I wrote down earlier, that the nilpotent sends the ith subspace into the ith subspace of the flag. And it has two projection maps, one onto the complete flag variety, just because, I mean, this is a consequence of the fact that it's the cotangent bundles. It's a vector bundle on the complete flag variety. So this map realizes it as a vector bundle. So in particular, this space is smooth because it's a vector bundle over something that's smooth. But it also has a map down to the nilpotents by forgetting the flag and just remembering the nilpotent. In this map, rho is called the Springer resolution. It turns out to be a resolution of singularities of the nilpotent cone. And so where does the name Springer fiber come from? Given some element of the nilpotent cone, you can take the fiber over it, over this map, and that's the definition of a Springer fiber. So the Springer fiber is the Springer fiber over this nilpotent matrix, maybe I'll denote it by SP now, dropping the delta. And since we're fixing the nilpotent, we can just run over complete flags. So it's the space of all complete flags. Such that for this particular nilpotent, the nilpotent sends each piece of the flag into itself. So now we get a subvariety of the complete flag variety, a closed subvariety. And the remarkable thing about this space is, although the symmetric group does not act on the space itself, there is a highly non-trivial action of the symmetric group on its cohomology ring. So Springer defined an SN action on the cohomology of each fiber of this map. And I wanted to take a little bit of time to explain how that action works, or really, at least how to construct it. And maybe the effect will just be like understanding that it's a non-trivial construction, but that's okay. So how do we construct this map? Or how do we construct the action? On the cohomology of every single fiber of this map. So first, we extend the map. So GLN, let me say GLN is the space of n by n matrices. Let's say with complex entries. And we can include nilpotent matrices in all n by n matrices and extend the map to some row prime, where we define this upper thing, the GLN tilde, as basically the same definition, but allowing ourselves to use any matrix instead of just nilpotent matrices. So it's pairs of flags and matrices such that X sends VI into I for all VI for all I. And this isn't quite enough to see where the symmetric group action is geometrically. We have to specialize a little bit. And the way that we're going to specialize is to what's called the regular semi-simple locus. So sitting inside of n by n matrices are the regular semi-simple ones. Regular semi-simple, meaning that X is diagonalizable. So it's similar to some matrix where you just see the eigenvalues along the diagonal, and such that any two eigenvalues are distinct. So diagonalizable with distinct eigenvalues. And then we can extend the upper space in the similar way as before. Just now restricting ourselves to only the regular semi-simple ones. I called this row RS to distinguish it. And so essentially we see like two different pieces inside of this larger piece. This one is closed inside of all matrices, and it turns out that the regular semi-simple ones are open within all matrices and therefore also dense inside of all matrices. So they make up almost everything. Every matrix is a limit of regular semi-simple ones. And almost as a consequence, like almost every fiber here is like a limit of fibers over here because of this dense property. And so what's special about the regular semi-simple part? So given some regular semi-simple, and given some flag in the fiber, that means that XVI is inside of I for all I. And now here's where we use the regular semi-simple property. So since X has these distinct eigenvalues, it has distinct eigenspaces. So the eigenspaces of X are all one-dimensional. They're all eigenlines. So let's say L1 through L are the eigenlines, meaning XLI is contained in Li, and since it's invertible, equal to Li. And then since X sends Vi into Vi, and X is invertible, so XVI is equal to Vi, and also it breaks up as a direct sum of eigenlines. So what that means is, as you build up your flag, you're just seeing some permutation of the eigenlines. So there exists some permutation of the eigenlines such that the ith subspace is just the sum of the eigenlines given by that permutation up to the ith one in your ordering. Okay, so let me give a quick example here. I just chose n to be diagonal with distinct diagonal entries. And then the eigenlines for this one, since it's already in diagonal form, the eigenlines are just the coordinate subspaces. So the span of E1, the span of E2, the span of E3. And then the fiber over this diagonal matrix is just the set of 3 factorial permutations of those eigenlines. So, you have E1, then E2, then E3, or you could do E2 and then E1 and then E3, and so on. and you just get the 3 factorial permutation matrices that correspond to some complete flags. And so what is the SN action? It's just the permutations of these eigenlines. So permuting the order of the eigenlines defines an action of Sn. On each fiber. On each fiber. Sorry, not n. X where x is, oh, sorry, maybe I should stick to x for regular semi-simple things and n for nilpotent things. Yeah. And then this action basically extends to the entire map. So it's a fiber-wise action of Sn on the regular semi-simple locus. Or in other words, another way of saying this is that this space is a covering space of the regular semi-simple matrices with deck transformations isomorphic to Sn. So it really is a geometric action on, at least on the regular semi-simple part. And for experts, so if you're an algebraic geometer or a geometric representation theorist, well, if you're a geometric representation theorist, you already know this fact probably, that the way that you use this is really that if you take the push forward of the constant sheaf of this regular semi-simple part, its endomorphisms are isomorphic to the group algebra of Sn. And so, okay, this is probably the most technical part of the whole talk series, I guess. But really just motivation for like, how do you construct these things? Where are these permutations coming from? Why do we expect that there should be some action? So what I've told you so far is, yeah, an Sn action on the fibers here. And then the idea is to extend the Sn action to fibers here, except you can't really do it on the actual fibers. It ends up being an action on the cohomology of each fiber instead. And then you can restrict to the fibers over nilpotent matrices. So yeah, this next line, these next like 3 lines are probably the most technical in the talk series and like containing the most hidden stuff. But using the theory of perverse sheaves, this action transfers to an action of the symmetric group on the cohomology of each fiber. of the middle map, the one for all matrices. And then in particular, you can specialize to fibers over nilpotent matrices. So Sn acts on the cohomology of the fiber over each nilpotent, which in alternate language is cohomology of the Springer fiber of corresponding to N. Okay, so now that I've said something very technical and geometric, like where does the combinatorics fit in? And like why do we care about the construction? The reason I really like this construction is because the functoriality of how it's constructed allows you to do the combinatorics in the following way. So let me just give a notation for the Jordan type, say call it mu. Then using another affine paving argument, you can check that the Poincare polynomial of one of these Springer fibers is the reversal of a related polynomial summing over row strict tableau. So row strict tableau of shape mu. And then keeping track of inversions of those row strict tableau. So say if mu is 3, 2, or to make Maria happy, I'll do French notation. Then one of these fillings would be earlier I was doing like filling in a rectangle and kind of leaving some cells empty, but in this version you put a label on every single cell such that it's decreasing along each row. And so such a filling P might look like maybe 3, 1, and then 4, no, 5, 4, 2 or something. Or in general, I could, it doesn't have to be column strict. Yes. Anyway, but not necessarily column strict, but row strict. And then inversions are looking at attacking pairs and counting inversions among the attacking pairs. Or alternatively, if you like Hall-Littlewood polynomials, this is the result of taking the modified Hall-Littlewood polynomial and taking taking the inner product with h1 to the n, or meaning the m1 to the n coefficient of the modified Hall-Littlewood. And then, so that's just the m1 to the n coefficient. How do you get all of the other coefficients geometrically? It's in terms of taking invariance. So let me explain that briefly. So given some composition of n, you have some partial flag variety. So the partial flag variety is defined I gave an example earlier, but in general, it's flags of subspaces. So Vi is in C to the N. And the dimension is the dimension of the ith quotient is equal to alpha I for each I. So jumps, the composition tells you the jumps in dimension. And you can take your Springer fiber, which sits in complete flags, and project it down to partial flags. Essentially, you just get partial flags with this extra condition that NVI is contained in VI. And then this projected version tells you information about the invariance. So the nice property of the symmetric group action is that in order to compute the Poincare polynomial of this projected, when you compute the Poincare polynomial of this projected version, you get the Hilbert series of the invariance under the corresponding Young subgroup. But then how do you phrase invariance in terms of symmetric functions? This is just the same thing as pairing. So basically the cohomology represents H mu tilde. And then when you take invariance, you're just taking H mu tilde and taking the inner product with H alpha. Or in other words, the M alpha coefficient of H mu tilde, or combinatorially, it's the reversal of what you get by summing over the same kind of tableau. So P rho strict and shape mu, but then content alpha, meaning when you're doing your labeling, use alpha 1 many ones, alpha 2 many twos, and so on. So that's basically how the geometry of Springer fibers relates to the representation theory or the symmetric function theory. So the moral is projecting to partial flag varieties is corresponds to taking invariance, but because of the functoriality of how these things are defined. And maybe since there's a little bit of time left, should I stop for questions or should I maybe say like a teaser for the next one?
It's up to you.
Okay, let me give a teaser for the next one. So the next goal is to, in order to use the Springer theory, thanks, Andy. In order to use the Springer theory, we need to relate these delta Springers to all of the constructions I said above, with these resolutions of singularities and then Sn acting on fibers of some map and transferring it over. And the way that plays out is basically you can adapt it or you can relate it to what are called partial resolutions of nilpotent varieties that were invented by Borjo and McPherson, and they have something to do with the skewing formula. In fact, when Maria and I were originally working on this, we were working on the combinatorial side for like a long time and getting like partial results using combinatorial methods until we realized the geometric connection or at t equals 0, and then used these Bornholm-McPherson constructions to prove the whole t equals 0 skewing formula. And then later on, we found the connections to the beautiful work of Blazek, Kanan, Morse, Poon, and Seelinger. So yeah, essentially what happens is, so I told you what this map is, n tilde to n, the Springer resolution, but for each composition, there's something sitting in between. And the thing sitting in between is basically the same definition, but for partial flags of type alpha. So NVI is contained in VI. And this thing sits in between the two. And the idea is that this space has a stratification into tuples of partitions, and you can restrict the map to each stratum, and the delta Springer fiber turns out to be a fiber over one of these, basically over this restricted map. A fiber of this restricted map over that particular nilpotent with Jordan type equal to the rectangle. And then we can use Bornholm-McPherson's theory to derive the skewing formula, the t equals 0 skewing formula. So that's what I'll explain next time.
Thank you so much, Les. Thanks, Sean. Great talk. Any questions?
Thanks, everyone.
All right. Doesn't seem to be having any questions. I mean, I understand that we have questions in between already. All right. So if not, then that's thanks, John, again. And we will resume again next Tuesday. Just remind everyone again, there's no IPAC on Thursday, so we'll have a break. But then afterwards, we will have Sean again to continue with the lecture series. Thank you so much, everyone. Bye.
Thanks, everyone.